Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Design, Test, and Repair Methodology for FinFET-Based Memories, brought to you by Synopsys, Tech Online, and broadcast by UBM. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, you can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window, and then click the Submit button. At this time, we recommend you disable your computer's pop-up blockers. The slides will advance automatically throughout the event, and you may also download a copy of the slides by clicking on the Additional Resources button located below the presentation window. If you're experiencing any technical problems, please visit our webinar help guide by clicking on the Help link below the presentation window. In addition, you can contact our technical support helpline, which is also located in the webinar help guide. And now, on to the presentation, Design, Test, and Repair Methodology for FinFET-Based Memories. Discussing today's topic is Yervant Zorian. Dr. Zorian is a Chief Architect and Fellow at Synopsys. Formerly, he was a distinguished member of the technical staff for AT&T Bell Laboratories, Vice President and Chief Scientist of Barrage Logic, and Chief Technologist at Logic Vision. He is currently the President of the IEEE Test Technology Technical Council, or TTTC, the founder and chair of the IEEE 1500 Standardization Working Group, the editor-in-chief emeritus of the IEEE Design and Test of Computers, and an adjunct professor at the University of British Columbia. Welcome, Yervant. I'll now hand it over to you to begin today's presentation. Yervant?
Thank you, Chris. Hello, everyone. This presentation is about FinFET, is about FinFET memories, and I will be touching on design, test, and repair aspects. Initially, I'll touch a little bit on the design side and then concentrate mostly on detection and repair issues, which of course have major implications on the quality and the yield of our FinFET chips today. And then I'll summarize with a couple of additional comments towards the end. As we know, FinFET technologies are taking quite a good popularity these days. We do monitor the complexity of chips as they go forward and the technologies being used on different applications. And we see that as the time goes, FinFET is catching up quite fast. This shows the initial designs and how they ramp up. So from 22 nanometer and below, we have seen FinFET becoming popular. We'll concentrate on that today. We're not talking about FDSOI, even though that has also some space in the scale complexity these days. With FinFET becoming popular, let's compare for a second how does it do compared to planar technology. The planar technology had a two-dimensional interface, if you want, a channel between the gate itself as well as the source drain interface. And now with the FinFET, we have turned that into a three-dimensional one. These nice thin fins that you see, the first one in the middle with a single fin, provides us the ability to control the channel much better. This green gate will be able to control the channel and with that give us multiple advantages. And of course, if we have multiple of those fins, that will give us even more granularity and better results. And today, the FinFET transistors do contain 2, 3 fins, and they may go even higher as we move forward. Now, what are these advantages? The advantages have been shown from early days when Intel started showing us certain advantages in 2011. This is from their IDF presentation, where we see these two key elements. One is the fact that we need lower operating voltage in order to run those transistors, and that lower voltage is quite drastically low, in fact. And then we also see faster devices, and that has to do with performance. So the lower operating voltage, of course, ends up requiring lesser power, so that's power reduction. That can go up to 50% in many cases. And also the speed of the device, the performance improvement, if we are at the 0.7 volt level, we can do 37% better performance compared to the planar technology. So both advantages in P&P, that is performance and power, give us a good advantage, and that's a key reason for FinFET being adopted today. For a second, if we again look at the advantages in more detail, we see that this scaling can be enabled, can continue with us, and the leakage will become less in this case because of the voltage advantage that we saw, as well as the variability will be less, of course, and these two will provide us nice advantages that we suffered from in the planar technology. Now, this brings with it certain considerations. And those considerations, first of all, start with making FinFET manufacturing a little bit more expensive initially. As we move forward, of course, that will probably go down, but the initial step is definitely there. Also, the width that we're playing with on the device side, it is quantized because you can have 1, 2, 3 fins. Every time you add a fin, it is quantized in terms of additions. So the granularity of additions is by number of fins. Also, there is an issue of heat. This self-heating of the fins also has complications, as we will see later on. The fact that they are not entrenched in the body itself, but they are in a three-dimensional way, sitting there with some self-heating possibilities that will give us certain disadvantages as well. Will be shown in degradation, in aging, and of course, having new mechanisms being built, we'll see losses in yield initially, so we need to be able to contain that also with solutions that take care of yield, as we will see later on in terms of repair and so on. Now, this will have implications on the users, but depends on which users. So with FinFET becoming popular, the implications will be mostly on the foundries who are making this happen, building this metal one layer, building the transistors, building the fins in a healthy way. Also, it will impact the IP designers while they're designing the standard cells or their memories. They need to take care of these newer structures and build them properly in it. But it will be lesser of impact on SoC designers. So SoC designers will use the libraries, will use the memories, but their flows, their tools, and so on will be almost similar to what we have seen before. So the implications are far more on the foundries, a little bit less on the IP designers, and far less on the SoC designers. Now, on SM itself, of course, it will have, as I said, implication on the SM designer, but it has some good advantages as well. The performance and the lower leakage are good advantages, and this lowering of the operating voltage has also some nice advantage. But we will see that there are some static and noise margin issues which are better. Also, the variability side will be better. So the process variation that we used to worry about much, it is less in this case. Now, in terms of ecosystem, in terms of tools that are needed while doing the work, extraction, simulation, and so on, it's worth mentioning that Synopsys in this case has all the necessary steps, all the necessary tools that can be utilized throughout the design stages to realize a new FinFET design. With that, we have built a set of expertise in various aspects from the lowest level up to the automation tools. While doing so, we have built multiple test chips with different memories on different FinFET manufacturers. So there are multiple FinFET manufacturers, several of which shown here, with whom we have done our memory test chips, and we have utilized our test and repair solution. In there, we have about 30, and we have optimized the solution as an outcome. The solution that we deal with, many of you know, it is a DesignWare IP called the STAR memory system. The STAR memory system stands for self-test and repair for memories on chip. The self-test and the repair are necessary components for some time now. We started in the earlier days from 180 nanometer and moving today to 10 nanometer while utilizing more advanced versions of the star memory system. So this system basically is the purple part in this box in the middle. The purple part contains RTL blocks that get generated from the star memory system IP compilers to deal with individual memories. So where you have SRAMs, dual port, single port, register files, one port, two port, ROMs, and so on, what we do is we provide nice purple boxes that we generate that directly interacts with the memory, a processor that deals with multiplicity of wrappers, as you see there in the middle, and then the processors together do report to an on-chip intelligent box called the Star Memory System or SMS server. And this server provides the necessary schedule, the necessary handshake, the interoperability from the external world via a JTAG tap to the internal world to the different processors. Now those processors have to be intelligent enough to handle the technology on chip, to handle the defects in terms of detecting them, to handle defects in terms of diagnosing them and repairing them. So all of that is in these purple processor boxes that intelligence needed for that. Now, of course, with the Star Memory System, for some time we provided the automation needed to generate, to insert, and verify for designers, and for post-silicon purposes to do the pattern generation, the analysis of results, the classification of faults, finding out exact locations, and so on. Now, all of this had to be mapped on FinFET technologies. We had to look at the FinFET technology and see how we can update our purple boxes accordingly, how we can update our external intelligence, the external software for post-silicon. Now, to do that, what we have come up with a flow that understands the memory design, understands the silicon, and results in doing that upgrade necessary. So the advantage that we had is that we were close to the knowledge about memory design, working with a large number of memory designers inside our companies and outside as well, having early access to process parameters, understanding the process from very early stages. For the last 3 years, we have dealt with multiple FinFET manufacturers, understanding their bit cells, and also looking at their models, validating them, and then dealing with the silicon, dealing with the test chips, and interacting with the silicon directly in our silicon labs. So having leverage or having access to the memory designs, to the process technology, to the models, as well as to the silicon and its characterization, helped us a lot do our work, our homework, let's say, on understanding FinFET defectivity and creating a solution for that. As a result, today the Star Memory System is used by multiple types of users. Some are the process developers that use it to characterize, to understand the process itself. This is for manufacturing. The second is for IP qualification. The IP developers do use Star Memory System for qualifying, for characterizing the memory IP itself. We have done this for our Synopsys memories for a very long time, for over 14 years now, with every test chip trying to characterize and qualify the test chip with Star Memory System. Now, of course, SoC designers would use it as well to incorporate it in the design and also use it for analyzing the chip later on. That's the SoC test and repair advantage. And the field reliability, we're seeing more and more utilization of this solution, especially now with FinFET. We see various problems that would happen during the lifetime of the chip, whether they are soft errors, whether they are aging-related matters that would need the Star Memory System to be used later on systematically, either periodically, on power-on, self-test, self-repair techniques, as well as ECC-oriented online test and correction activities. And we'll talk a little bit about that also towards the end of this presentation. Now, what we do with the Star Memory System in FinFET is not only meant for the entire chip, but we also have several other things there on chip that we need to provide. The chip would contain logic blocks, would contain interface IP blocks, AMS blocks, and so on. So Synopsys provides a comprehensive set of solutions, which is comprised of different products that are used for different types of blocks. For logic blocks, we have DFT Max and Tetramax. For memory blocks, of course, Star Memory System is the concentration of our presentation today. The interface IPs, we do have their own best engines, but they all collaborate with the next level solution that is a star hierarchical system. So having an excellent solution for each block is important, but also connecting all of those into an umbrella solution that interacts with each, collaborates with each, and finds out the SoC level access and porting solution, which is a star hierarchical system, is needed, especially on these newer FinFET chips where we have lots of complexity. Such a star hierarchical system will be needed to connect the memory infrastructure, the logic, and elsewhere. So I'll touch on this a little bit towards the end of my talk as well. Now, what does Star Memory System today do? It covers numerous chips. We have seen its presence widely. It touches all these new types of defects that we'll cover together shortly. It provides a solution for individual memories, also for groups of memories. So we'll talk about individual and groups of memories as we move forward, and we'll see some examples of its usage there. And it is used in different places, from IoT all the way to automotive industry. So the applications are a wide range from different levels of reliability requirements. And therefore we meet various reliability needs up to the automotive level ISO 26262. Now, these range of applications are there, but we need to first of all understand the silicon. Understanding silicon means understanding defectivity. While at the Planar technology, we looked at process variation in detail, understanding how do they happen in silicon, how they get manifested, and how do we need to detect them and fix them. Also, we looked at resistive faults initially, looking at how opens and shorts can be resistive. That is, they are not detected immediately by a single operation, but rather they need multiple operations for them to be detected. And we moved forward on different blocks of the memory, up to the addressing block, looking at what's in there, which brought us to a set of solutions that can be applied now on FinFET. A set of solutions in terms of investigating, in terms of analyzing, looking at defectivities, developing test sequences and algorithms, as we'll see in a second. But all of that cannot be only theoretically done. They have to be done also with the silicon in hand. And therefore, we had to go through numerous test chips on various foundries, testing our solution and identifying its strengths and weaknesses and improving it further. So these are the 30 test chips that we have done so far on different foundries. Now, how is FinFET different than other technology is different than the Planar technology? If you look at FinFET, you would see that there are fins, and here we're showing just one fin per transistor, and you imagine this having multiple such green fins next to each other. And with those fins, we have different phenomena that happen elsewhere as well, that is opens and shorts. But in fins, the behavior could be different. And those opens and shorts of fins, they can result in fin opens, in gate opens, in fin stuck ons, in gate to fin shorts, and so on, each of which can be a full open or short, or can be resistive ones with different resistive values in between. Now, some of those are realistic because physically, looking at the cell, they would physically happen. Others will not be realistic. Therefore, we do categorize the realistic and non-realistic ones according to the physical structure of the transistor. We looked at the parameter size for that. We look also at threshold voltage variations, again, to ensure that that is covered properly. Now, these are just samples of the different defects that we look at in FinFETs. Now, we don't look at only transistor level. This shows us that we look at 4 different levels. The first is what's happening in the transistor, such as the fin open or fin gate shorts. But we move on to see that we do have also the memory level. The memory is 6 of those transistors together. So we look at the memory cell, and we analyze in the memory cell, for instance, the open in cell internal nodes and how that happens and what does it result in. Then we move on from transistor to memory cell to the memory array. This is level 3, we call it. And we analyze level 3 by looking at opens in bit lines, short between the word lines, and so on and so forth. And then finally, at the block level, that is the memory block level, and we have surrounding blocks around the array itself, such as the address decoder, where we look at opens, and so on there. We look at the write drives, we look at the sense amps, and analyze the defectivities in them. Now, in each one of these levels, we look at individual failures, multiple failures at the same time. Here, for instance, you look at the left-hand side, you see a short between 2 sides of a fin, as well as shorts between 2 fins. You see opens of different fins on the figure on the right-hand side. So analyzing these and analyzing their behavior is very important. As I mentioned, we look at them in the layout of the cell, of the memory cell, and we look at the adjacencies, and we look at accordingly on the opens and the shorts that would happen at the memory cell level. So mapping it is important. How do we do that? We do that based on defect injection. The defect injection that we have is based on the GDS itself. So we do defect injection on the models, on the SPICE models as well, and using a defect library for each one of the libraries that we deal with. And there we look at how they are behaving. We have repeated the defect injection for transistors and analyzed the results. We did that for all the providers of FinFET on 16 and 14, whether they're IDMs or foundries. Also, we looked at the comparison of those with the Planar technology. So with the Planar technology of 45 and 25, we're trying the same issues at the memory cell level, for instance. We looked at the comparative outcome in terms of behavior. Of course, we compare that simulation on the GDS and level, as well as the SPICE level, to the silicon data itself. So the silicon data obtained is also compared to it. This defect injection results in telling us how each one of those defects is behaving. Now, the behavior is one thing. Next is the test sequence that relates to it. So we develop test sequence. We call this process TSI process. This is test sequence identification, and also the abstraction as a fault model, so determining which fault model it belongs to. So for each one of those defects, we create the test sequence corresponding to it. And then there could be a couple of TSIs that are needed. And also we look at each TSI and what are the conditions under which it will be detected, okay? As well as the fault model that it will correspond to. Now, some of the cases will be fault models that we already have seen in the Planar technology. In some other cases will be new ones. Here is an example of a new one, and we have seen multiple new behaviors. So there are many new fault models that we had to identify because of the FinFET technology. This is a dynamic deceptive redestructive fault, where what's happening is that it is a deceptive redestructive fault, but a dynamic one. That is, one write, one read will not be sufficient. We need multiplicity of reads because it's happening due to the open in a fin. So a fin open with a low resistance would result in this behavior if that fin open, if that fin itself is in a pull-down transistor sitting in the memory cell. When I do a write 0 operation and I try to read it, initially you see those multiple reads will give me some intermediate level, but they are not able to flip it yet. But after a number of reads, in this case specific low resistance case, after 7 reads, the cell content is flipping. And that does happen, and the content would flip. It's a deterministic fault. It's not lock-based. And that flipping will convert the cell content. And we need to detect that. We need to know if this specific open in the fin exists in the fin that we have created in our memory cells. And for that, I need to apply a certain sequence. And the sequence in this case happens to be 7 consequent reads. Those reads would depend, the number of those reads would depend on the frequency also, so that those 7 were under a certain frequency. If the frequency of the test is higher, for instance, if it's 1.2 gig, then 4 consecutive reads will be sufficient to flip the content of the cell. If I have a lower frequency, for instance, if it's 800 megahertz, then 8 consequent reads would be necessary, and much more if it is lower than that. So this fin open is detectable, is detected. It needs a loop of operations. So in your TSI, the test sequence itself, you need the multiplicity, and that multiplicity is a loop that we need to build it into our system. That is the creation of the loop itself. So the length of the test, and it depends on the frequency, and also the voltage and the temperature are important elements in doing so. This is just one example of a FinFET-specific failure. There are multiplicity of such examples that we detected, and also multiplicity of cases where the planar faults do happen. Of course, there was also the category where certain planar-oriented faults would not happen or did not happen in the case of FinFET technology. What we observed, though, looking at the bigger picture, that dynamic faults are more prominent in the FinFET case. That is not static faults where you would immediately find out the results, but you need multiplicity of reads, multiplicity of writes, so loop of operation is necessary. So in the case of FinFET. Now, on the process variation, as expected, we also saw through our results that the process variation issues are far more stable in FinFET compared to what we used to see in Planar. The static single-cell faults are similar to the past, so there's not much different in terms of static single faults do happen the same way as Planar technology. And we saw also an important factor, that is the stress corners have far more implication in this case, where the vast majority of the faults in the past were detected under multiplicity of corners repeated. In this case, there are certain types of faults that happen only under a single corner and not others. By corner, I mean voltage, temperature, and frequency levels. Which means that if we need to maintain the proper quality of our chip, we need to have multiplicity of voltage, temperature, and frequency points under which specific segments of algorithm need to be run. And we have done all that homework, so we know exactly under what voltage, what temperature, and frequency the changes need to happen. And test escapes will not be possible in that case, given what we have seen. So test sequences that we end up collecting for a given corner get combined together under our synthesizer. We have a synthesis engine called the tag, that is a test algorithm generator. The tag will combine together small test sequences for individual fault types, and then will create a minimum test algorithm. So the idea is to have minimum test length to minimize the test time, to minimize the test cost. So what we do is we combine those together automatically via this green box called the tag. So the tag these are all automated processes, from the injection to the test sequence extraction to the tag itself, and we create different pieces of algorithms, if you want, for different corners that are needed. As a result, what we see is in this advanced flow, we see that we have the different 4 levels of defect injection that we do initially. Then we create the pool of test sequences for different conditions. And then we have the test algorithms. We have different partitions of them that are run under different conditions and for different probabilities as well. In the star memory system, we have already implemented this looking at the different providers of FinFET, and gladly, we saw wide commonality between them, even though the bit cells are different from each other, but the behavior of those bit cells by different foundries were not drastically different from each other, were quite similar, so that was a nice thing for us to notice. And therefore, we have augmented our solution with the FinFET algorithms in them. The good thing is that the star memory system does have also programmability in it. That is, you can come in from the JTAG port of the chip through the server, to the processor, and update the algorithms that sits in the processor. So the programmability is important in order to allow you to modify the test sequence itself or the test algorithm, either for different corners or for debug and diagnosis purposes, for upgrade purposes, and also to change the loops if you want to count the loops 4 times versus 7 times versus otherwise. You can do that whole thing via the programmability. Of course, that's not sufficient. With the programmability, your engine needs to be able to do these things. So the SMS engine, the processor itself, needed to be up to date in order to allow this programmability to come in, to allow the loopings to happen, to allow the special addressing sequences to be created. So the specific fault models, their sequences and algorithms had to go hand in hand with the hardware, with the IP box, the SMS processor that sits in there. And we needed also to compare all of that with the silicon data. So those programmabilities and the SMS engines were validated on silicon as well, on this multiplicity of test chips that I mentioned earlier. With that, we were able to do our diagnosis of multiple levels. So our diagnosis starts by showing which memory is failing, which logical address on that memory is failing, which physical address that is. So it fits us the information to understand which physical XY coordinates the failure was, and also the defect classification means that if it's a bad bit, double bits, 4 bits, quad bits, a full row or full column, all of that get identified with our software sitting outside the chip based on what was extracted from the SMS engine on chip. So with this FinFET solution, we were also able to do the fault classification, so which type of faults were happening there. So in short, what we're trying to do here is we're trying to look at the memory design itself, the cell designs that is, do the injections, do the extractions, look at the models, and accordingly create the test sequences and the algorithms. A user needs to have the algorithms and use them, but use them under the different stress conditions necessary, that is the different corners necessary. The SMS engine itself, while we upgrade it to be able to handle the different test and diagnosis features, but at the same time, we also make it programmable for it to be uploaded as necessary. Now, the memories that we have are of different sorts, and they come in different flavors. In FinFET, we are seeing far more the possibility of optimizing timing by having a pre-inserted groups of memories with scheduling, with BISMUXs already in their places, and having a shared test bus that comes out. Different processors are doing that, as well as different custom data path creators are using that. We have seen that from ARM cores, where ARM CPUs have used these shared test buses, as well as now lots of data passes are also doing this insertion of muxes and buses in advance. For this, we have created a solution that is called the MMB processor. It's an SMS multi-memory bus processor that deals not with the wrappers directly, but rather with the bus port directly, this red box that sits there. So the MMB processor handshakes immediately by reading the information from that gray box, understanding the memory specifics as well as the configuration of the right bus and generating an MMB accordingly. Now this has various advantages, and we're seeing this happening in multiple FinFET chips these days. Performance advantages, because the muxes have been inserted in an optimal locations. We see lower area because the wrapper is now incorporated into the processor design, as well as we see ease of integration because we have the ability to read directly the core content and accordingly specify how the SMS needs to be configured. Now, we have seen this being implemented on different data paths. There is a work that has been done by Marvell Semiconductor. We have published some of that already. That is, Marvell has published it, where they have designed their own SMS wrapper into the data path and created the bus port and directly interfaced with the MMB processor. We have seen it also used often in different cores, not only on the test side, but also on the repair side. So we have augmented the bus with a repair component that extracts the memory redundancy information and passes the control to the MMB processor. And with that, MMB processor for this FinFET chip doesn't only detect and diagnose, but also repairs the memories directly. Another element that we are seeing in our chips today, in these complex chips with FinFET, is the fact that there are some DRAMs, some external memories, that are sitting outside the chip. Those external memories need to be interfaced. But the fact that the chip is fast, and especially the interface itself is fast, let's say it's DDR4 or HBM or wide I/O, it is hard to come and intercept the signals between the green boxes and the SoC sitting below. What you need to do is you need to have an engine that sits in your SoC and from there interact with the DRAMs that are sitting outside, or SRAMs for that matter. What they do is they allow you to provide the test and the diagnosis necessary for that purpose, and the handshake will allow us to do the necessary high-speed connection, and with that high-speed connection, find out where the problems are, and of course, replace them accordingly. So find out where the problems are means diagnosis. If you have multiple memories, find out which memory is failing. If you have multiple interconnects, find out which interconnect is bad. Because replacing that whole unit is very expensive. Maintaining the expensive SoC and changing the interconnects or the memories is much cheaper. So what this solution provides us is the ability to identify which interconnect, identify which memory at the high speed, and that, of course, as a result, find a good repair solution for it while your DDR SoC is, while your DDR port is interacting with the memories or your HBM, and accordingly be able to solve the problem. So FinFET chips, again, do have these kind of memory issues these days. Now, talking about the next step, that is repair, is important as well, because as we detect failures in the memories, we need to repair them. Now, all the embedded memories these days do come with redundancies. Often they come these days with row and column redundancies because they are needed in order to be able to fix the memory and therefore the SoC. What we do is we provide a nice solution for repair that is integrated into the same star memory system. While the FinFET defects are being detected by the algorithm, at the same time they're feeding to the same engine the information of the location of that failure. And whether it can be detected by a row or a column is decided by that same engine as well. So the decision-making process for rows and columns is critical in this case. And what we do is we use cumulative repair. That is not only repairing under a single corner, since the chip will be more and more detected or tested on the different corners of temperature, voltage, and frequency. What we need to do is we need to provide repair or yield optimization for each one of those corners. And here the star memory system is equipped to do that as well in order to help us do repair for one corner and then augment it at the next corner and so on cumulatively. Now for that we need to have, of course, the necessary infrastructure with if users that are sitting there with multiple zones that handle this cumulative repair. Now all of this, the test part, the diagnosis and repair, can also be repeated in the field, that is upon usage. So because aging is critical these days and things would happen during the life cycle, what we need to do is we need to find a good solution, and here it is, a periodic repair possibility, either upon power up or time-based periodic repairing. Now, also, we know that there are other factors that do happen, such as MBTI, for instance, negative bias temperature instability. It is a serious matter in the case of FinFET. We have done good analysis for that, and we found out the different aspects that are resulting in MBTIs. It is mostly temperature-based. Okay. So there's a deterioration that happens from the temperature range under which FinFET is operating. PBTI came out to be negligible, but MBTI is considered serious, and therefore this temperature implication on deterioration need to be taken care of. Also, soft errors, as we know with planar technology, existed, and as we're shrinking technology, the cells are becoming closer and closer to each other. What's happening is that a single bit failure now is turning into multi-bit effect, and the multi-bit effect need to be not only detected but also corrected, and therefore multi-bit correction becomes an issue, and therefore we needed a solution for that as well. So we have developed a solution on the star memory system that is called a star ECC. This one will allow us not only to do classical ECC, which is multi-bit detection and single-bit correction, but rather multi-bit correction as well. So FinFET solutions would require these as well, as long as the reliability is important for that chip and the lifelong health is critical. So repairing periodically, being able to take care of the aging and the software problems as well, whether periodically or online, are part of the FinFET solution. Finally, the same FinFET chip, besides memories, would also have other mixed signal IPs. Other mixed signal IPs meaning different PCIs, USBs, DDRs, PLLs, MIPIs, and so on. Each of which needs to be, again, self-tested, each of which need to be, again, detected and repaired. With repair, we mean calibration and trimming. And all of that needs an infrastructure. This pink infrastructure complements the SMS infrastructure that we saw earlier. So besides SMS, there is a complementary piece here called the star hierarchical system that allows us to test, debug, as well as fix those mixed signal IPs beyond memories. So thinking of beyond memories is important in those chips, and with that, taking the information from the small set of IPs or large set of IPs that test information, which patterns, which IOs need to be taken care of, which test modes, and so on, capturing it into a model that the star hierarchical system automatically recognizes and accordingly builds on it the SoC solution. It's a hierarchical solution as you would expect. It will take an IP with its patterns and from one level to the next level, from an IP level to the subchip level, create the access, interface, and build up the patterns at the next level. Same thing from a subchip to an SoC, again carrying the access as well as the patterns together to the next level. So SHS, this purple part of the diagram, allows us to build it up and connect it with the memory solution for FinFET that we have shown earlier. Of course, there's much more detail on those things. Today it just mentioning them under this umbrella. Where do we stand today? Today we stand at the 14, 16 level FinFET solution, looking at the 10 nanometer cells and their defectivities, analyzing them. And with that, we have put an effort and continuing that effort to understand the silicon, to validate it. We have had a large number of chips that have used our solution in the past and continue to use today with very good success so far. So we see first time right silicon coming out, and that encourages us to continue our work. Moving forward, what we see is that we need to do a multiplicity of things. We need to continuously look into the functionality that we're adding compared to the area. So reducing area, optimizing the test itself in terms of the quality of test on which we have concentrated today together, as well as optimizing yield. Again, we talked about that as well in terms of repair, aging, correction, and so on. So quality and yield are our concentration while building the necessary automation for fast ramp-up, that is fast design and fast silicon debug at the same time. With this, I think I completed my presentation, and I'll be happy to handle the questions. Chris?
All right. Thank you, Yervant. Great presentation. Before we start with our Q&A, please fill out the feedback form that is opened up on your computer. To complete the form, please press the Submit Answer button at the bottom of the page. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to serve you better. And now we're going to move on to our question and answer portion of the event. As a reminder, to participate in our Q&A session, just type your question into the text box located below the media player, then click the Submit Question button. Please note we're going to try to get to as many questions as we can in the time that we have left, but if we don't get to your question today, that someone will get back to you via email. And so now let's move on with our first question. Looks like our first question for you is, Yervant, would the STAR IP results also be integrated with Yield Explorer?
The answer is yes. Yield Explorer, for the larger audience, is a Synopsys product that handles yield data, does the analysis, the classification, the visualization, and so on. And as we do analyze the outcome of the testers, that is the SMS or the Star Memory System Yield Accelerator does the debug and diagnosis on the outcome, interprets the results, finds out the exact location of the defects, as well as classifies the faults and so on. All that data would pass to Yield Explorer, and Yield Explorer will be able to handle the classification of those, will be able to handle the statistics and the visualization with large scale for many chips, for large volume wafers and lots.
All right, and the next question, and forgive me if I get this wrong, but do you receive the defects injection from the various IDMs or foundries, or do you build it yourself? And if so, how?
Yeah, we do build it ourselves, but we validate it with the IDMs as well, because the cells, the bit cells, are typically, as you would know, they come from the manufacturers. So while the memories are done by us or other memory IP providers, the bit cells are common. So each foundry has its own 6 transistor bit cells that they characterize, they build, they model, and so on. So the defect injection that we do are on those bit cells on the validated models. So they are validated with the groups themselves, and we try not to really touch the inner side of the cell description itself, but rather build on the additional shorts and opens, the resistive ones above, and understand the behaviors with our high-end tools.
All right, thank you, Yervant. Our next question for you: does this memory solution allow the user to apply new algorithms, or are the algorithms hard-coded in the RTL IP?
They are both, in fact. So you can do both, that means. The FinFET algorithms are the algorithms that we provide through our yield accelerator, which is the tool that sits outside the chip. That is the software with a library of algorithms. Now, those algorithms, you can either program them in advance, and we have the ability to do that, and hardwire them in advance in the chip, and you don't need, in that case, to ship them later. Or not to do that, to keep short default algorithms in the chip, but augment it with the FinFET test segments that are sitting outside on your software. So you have the ability to put it either inside the chip from the beginning, make it part of your design, or scan them in and program the engine later on post-silicon. Both are possible.
All right, thank you, Yervant. Our next question for you. I'm interested in understanding how IJTAG interfaces to allow for direct parametric access to memory cells.
IJTAG has good capabilities in terms of accessibility, and we use IJTAG advantages in our infrastructure typically. While we build our hierarchy in SMS or in SHS, that is the star hierarchical system, we use the IJTAG connection mechanisms. We use the SIBs and the NIBs that IJTAG provide. In fact, what we do is we take advantage of all the IEEE TTTC standards that we have developed in an optimal way. So we look at what is the best of each, and we try to utilize them in coherence, in nice synergy with each other. For instance, we use IEEE 1500 for a long time to interface with the SMS engines. We use the IJTAG, which is 1687, from the core level to the chip level, all the infrastructures that we built. We also utilize JTAG at the chip level in order to access the tap. So all of them are in use in this case.
All right, we'll move on to our next question here. Would the SMS flow be the same for planar and FinFET nodes?
Yes, the flow is the same. So in terms of utilization flow, that is design aspect. Planning, generating, inserting, verifying whether it is planar or FinFET, we haven't changed. It's the same flow that is continuing. We are on the 5th generation of SMS, and we have a similar flow. In fact, the star hierarchical system has also the same flow. Now, in manufacturing, again, it's the same flow that you need to do, except you need to download or upload, I would say, the FinFET algorithm segments necessary if you would like to do that during manufacturing. Otherwise, you would have put them on the chip in advance. So the flow is the same.
Okay, and Yervant, how many types of memories are there in your test silicon where SMS5 is validated? And is there an overall picture to show it?
I don't have a single slide that shows all the types of memories on, but with SMS5, what we have done is we have dealt with the SRAM family of memories first, and now we have extended it further to few other types of memories, and let me say what they are. So with the SRAM memories, what we cover is the high-density SRAMs, the regular single-port, dual-port SRAMs, the register files, 1 port, 2 ports, the ROMs. And besides the SRAM family, we augmented it to CAMs. So SMS5 also addresses content addressable memories. It addresses small register files that are made of registers. Okay. It also addresses recently embedded flash. So we have augmented and we have announced that 6 months ago that now we are handling with SMS5 embedded flash as well. So that is covered too. And we do handle DRAM-oriented defectivity algorithms and repair for external DRAMs. So we also handle DRAM-oriented algorithms. So on our test chips, we have done the majority of those. Some others are not on our test chips, but on our partners and customers' test chips. We have seen SMS being used by multiplicity of memory IP providers and IDMs as well for their own internal memories. So as you know, IDMs and fabless companies have their internal memories, and we have a large number of them utilizing SMS for their usage.
All right. And our next question for you, does star ECC perform SEC-DED for multi-bit soft errors?
Yes. The star ECC is a programmable solution. While regular ECCs do Hamming code, and that is for single correction, as we all know, what we did with star ECC, we provided a solution that can do single, double, triple, 4, and it's programmable. So you decide how many bits in a word you want to correct, and it generates the necessary circuitry for that. It has several advantages of pipelining, insertion, and so on. But most importantly, it does multi-bit correction based on the memory information itself. So it reads the memory information, and based on that, it generates necessary code for multi-bit correction to the level that is requested. Now, different chips, different applications, whether they are in networking, in automotive, or military equipment, they need different levels of reliability. That's why we made the star ECC programmable for that purpose.
All right, we're going to try and sneak one more question in here real quick, Yervant.
Sure.
Are aging effects more pronounced for FinFET memories than planar process memories, and do we need new algorithms for targeting these?
Yes, aging effects are more pronounced. That is a fact, and as I mentioned, the MBTI is one of them, and we have seen the reasoning behind it. The deterioration is happening, for which we need solutions. Now, the algorithms are hard to change, because if the algorithms are used during manufacturing, the aging effect will come much later. However, you need to have detection later on and correction later on. So detection and correction of the lifetime is where you want to concentrate, not the manufacturing algorithms themselves.
All right, Yervant. Well, that was a fantastic Q&A session and a great presentation. That's all the time that we have for questions for today. Just as a reminder, if we didn't get to your question, then someone will get back to you via email. And for more information related to today's webinar, please visit any of the resources links opened up before you. Within the next 24 to 48 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. Additionally, you can view today's event on demand by visiting www.techonline.com. Once again, we'd like to thank you for attending today's webinar, Design, Test, and Repair Methodology for FinFET-Based Memories, brought to you by Synopsys, Tech Online, and broadcast by UBM. This webinar is copyright 2015 by UBM. The presentation materials are owned by or copyrighted, if that is the case, by Synopsys and Tech Online, who are solely responsible for its content. The individual speaker is solely responsible for his content and opinions. And on behalf of our guest, Dr. Yervant Zorian and Synopsys, I'm Chris Keach. We'd like to thank you for joining us, and we hope you have a great day.